In this video, I would like to discuss end of chapter question 4 from chapter 22 from the book Chemistry Cubed. And I will just read out the question. Suggest efficient syntheses for components 7 to 10 from benzene. More than one step is required in each step. Comment on the selectivity of any electrophilic substitution reactions. Okay, so we're actually having 4 target molecules in this case. One here, so nitro and alkyl substituted benzene, then a bromo-nitrobenzene here in the second case. Third target molecule is this bromochloro component, and the last case here is this component where we have like a nitro and azo group on our benzene molecule. So this is the molecules that we need to bring in. And yeah, our starting material is in this case benzene, so we have basically like a plain starting field, and we need to introduce, in the first case, we need to introduce an alkyl group and a nitro group. And yeah, so we can basically come up with 2 hypotheses. First, introduce the nitro group and then the alkyl group, or the other way around. And what is actually more beneficial? Let's draw the 2 alternatives out, and then we can decide which one is better. First this, or first the alternative with the nitro group. And what we can clearly deduce from here is that it's actually better to first introduce the alkyl group, because the alkyl group has a directing effect in 2 and 4 positions, so it actually favors an attack here opposite to it, so that's actually where we want to get our nitro group. Whereas when we introduce the nitro group first, then the attack would be favored in 3 positions, so in meta position, and that's not something that we would like to happen, because we want to have the substituent, the second substituent then happening here in para position, and this is not favored when we introduce the nitro group first. So what we actually try to do as our starting material here, as our first target intermediate, is like this ethereal molecule here overall, as you substituted benzene molecule. And how can we do this? Easiest answer is one of the Friedel-Crafts reactions, and we've seen also in the lecture series that Friedel-Crafts alkylation would not be the best case, because it would lead to polysubstituted products, because this molecule here is actually then more active for an subsequent Friedel-Crafts alkylation. So this is not something that we will do. Instead, we are taking the detour via the Friedel-Crafts acylation. So our molecules, our starting conditions that we want to use, is something that looks like this. So an oxygen atom here, and then here a chloro atom, and on the other side we are also needing a Lewis acid to activate, something that aluminum trichloride can nicely provide us with. So this is our first reaction, and our intermediary component here in this case would then be this acetophenone that we can see here. So, and then in the second step, we want to reduce it actually to get to this acyl group. What can we do here? We have also discussed this in lecture. It's actually the Clemmensen reduction. This is not something like an electrophilic substitution reaction, but just a normal change in oxidation state. And so I will just write Clemmensen reduction onto the reaction arrow here, and this would reduce our other component here with the carbonyl group to this selectively to this monosubstituted ethyl benzene. And in the last step, we just need to use our nitration reagent, so nitric acid together with sulfuric acid, and in this case our ethyl substituent helps us to push the nitro group into the para position. First, of course, due to the electronic effect, it's a plus I substituent, and the second reason is also the steric hindrance caused by this acyl chain here. It's partially hindering the approach into the auto positions, and that pushes the reaction even a little bit further into the para position. But probably we would also get the ortho substituted product, and then we would finally need to do like a cleanup step where we purify our product so that we in the end get our pure para-nitroethyl benzene here as our first target molecule. Good. Second target molecule is actually this bromo-nitrobenzene here. And the question here is again, which substituent do we introduce first? Let's maybe draw out the two alternatives first. So first the bromo group, or on the other side first the nitro group. And as we've also discussed in the initial question, it's probably better to first introduce the bromo substituent. The nitro substituent would again push our second substitution into the meta position, so here at the bottom of the ring or on the left side, and actually we have here a substitution pattern that looks like an auto substitution. On the other side, our bromo substituent is also slightly deactivating, just as our nitro group, but it pushes a substitution reaction into the auto and the meta position by providing electron density in form of its lone pairs to the electron to the benzene ring, and then we find this electron density here in the auto and the para positions. So actually our first target molecule is the bromobenzene. How can we do this? We are using bromine together with a Lewis acid, in this case maybe iron tribromide, to activate our bromine molecule, and then we receive our first target molecule. And then the second thing we need to do is, I will just move this a little bit closer here, is to add our nitration reagent, the same as we've seen before. That's nitric acid together with sulfuric acid. And then we would get the substitution in also, but also in para position. And then, as we've seen in the first step, we also would need to do a cleanup to separate our two products here, the also and the para substituted benzene molecules. But overall, this is how we could do it. Third reaction actually is like this chloro and this bromo substituted, also this meta substituted bromo-chloro benzene here. And yeah, the trick here, this is, yeah, we need to take a little bit of a detour, because either we can first introduce our bromo substituent, or what we could do is we first introduce our chloro substituent. But both of these substituents are actually 2,4 directing, so there is no way for us to use the directing effect of one of the sides to get the second substituent selectively into the meta position, what our target molecule requires. So we need to change something here, and then also take a little detour to maybe introduce first one of the groups, and then use a slightly different mechanism to transform one of the substituents. So let's first do that. And the best approach to maybe get this meta substituted product is to first introduce a group that is actually directing into meta position. A group that is directing into meta position is actually the nitro group. We have just seen that before, and the nitro group will, as we just see in a minute, will nicely help us to transform one of our substituents into one of these halogen atoms here. So we are first producing our nitro substituted product here. And how do we do this? Again, the answer is this nitration reagent, so nitric acid with sulfuric acid. And that is our first step. Now we can use the directing influence of the nitro group to push our second substitution, or our second substituent into into the meta position. How do we do this? We first use here the nitro group, and then we are using, in this case, we are introducing the chlorine substituent, so we are using chlorine together with Lewis acid to activate it, like aluminium trichloride, and then we would end up with something like this. Important to keep in mind here is that maybe this reaction needs a bit harsher conditions, because the nitro group is actually strongly deactivating for the aromatic core, and this addition of the chlorine molecule is actually also something that needs a bit of electron density, so we need to push a little bit harder by maybe heating the whole reaction mixture up a bit, and then also doing it for longer amounts of time. But in the end, we would end up with the meta-substituted product here. Of course, partially would also get the also and para substituted products, but only to a small degree as like the minor products. And this would be then our intermediary product here. And now we are having this nitrochlorobenzene here in meta position. So the already present substituents are in the right arrangement relative to each other. But now we still need to transform the nitro group into the bromo group here somehow. And how we could do that is by first transforming or reducing our nitro group with, for example, tin in hydrochloric acid into a amino group. The amino group is then very helpful to do a subsequent reaction, and this would actually look something like this, so the amino substitute benzene, and from there we can use the Sandmeyer reaction. That is where we first change our amino group into a diazonium salt, and then we are using copper 1 bromide to substitute our diazonium group here, the N2 group, to form this bromo substituent here. So the reaction conditions would actually be something like sodium nitrite together with something that protonates, maybe hydrochloric acid. That's the first reaction step, and then in the second reaction step we need to use copper bromide to get our bromine molecule substituting this here. And I can maybe also draw the intermediary structure that is formed here. That would look something like, of course, chloro substituent, and the other substituent would look something like this here, where we have a triple bond between these nitrogens and actually a positive charge. So this is this diazonium salt, and for charge neutrality reasons we also need to add a chloride anion next to it to basically neutralize the charge. So this would be the intermediary stage that's formed after the first reaction step, and from there we can then transform it with copper bromide in the Sandmeyer reaction. Okay, so you see quite a few reaction steps, and what makes this so tricky here in this case is actually the meta substitution pattern at this chlorobromobenzene molecule, because both of them are not directing into the meta position originally. So we need to take this detour via, for example, the nitro group. Okay, last reaction is actually looks a little bit intimidating at first. So we are somehow producing a very bulky substituent here, and this is something that we have not discussed in the video lecture series so far. So what we would like to do is actually first maybe make the molecule a little bit smaller so that it's easier for us to see what is important here. I will just take this over here for a minute, and then I will just delete this whole naphthalene ring here that looks like it's causing a lot of trouble, and we're just putting something with an R group here. So in the end we're just having this azo bridge here, and we're having a nitro group, and they are in para position relative to each other. So what can we do to introduce this? First thing, we need to think about where do we want to, which molecule do we want to start? And the first molecule we can synthesize is either, again, the nitro substituted benzene molecule. That would look something like this. Or the other thing would look something like the diazonium salt. This would actually look something like this here maybe. No, that's also not so nice. This, and then this. So maybe this is better. Yeah, potentially this diazonium bridge or this azo component here is a little bit better, because here actually we have a lone pair at the nitrogen, and this can be used to push subsequent substituent here, or an electrophilic attack into the para position, whereas the nitro group is again, as we've seen multiple times now through this exercise, pushing the follow up into the meta position. And this is something that we do not like, because in the end we would like to have the para substitution pattern here overall. So let's see how this sequence spaces out. I need to also have a look at the exact reaction conditions, because that's not something that's super obvious to see right from the start. So I also needed to prepare that for a bit. And we can see that here. So first thing is we would like to introduce an amino group to transform our, to get to our azo substituted molecule. How can we do this? Move this a little bit to the left. First thing, I will just shorten this a bit now. First thing would be to first introduce a nitro group. We've seen this numerous times. So nitric acid with sulfuric acid. And in the second reaction step, we are reducing that actually with tin and hydrochloric acid to produce the aniline molecule from that. That would then look like something like this here. Okay, so this is the first two reaction steps we actually need to do. And then we need to produce the diazonium salt. That is again done by, and let's get this out of the way here. This is actually done by using the reagent we have also just used in the previous reaction. So the sodium salt with hydrochloric acid, and then we are producing this molecule with the nitrogen-nitrogen triple bond. You can see that then here and here, and we're having the positive charge. I neglect now the of course present chloride anion for charge neutrality reasons. And this molecule can then be attacked by a benzene molecule, or not a benzene molecule, but a naphthalene molecule. So this is like these two aromatics coarse fused together, as if I've just drawn them. And we start with this hydroxy group here in this position, and then actually the hydroxy group favors the attack here right next to it, and that's why the attack happens directly here. And in this way we produce this azo group. I will just copy our target molecule so that we can use that later on and do not need to draw the whole structure again. Let's move that down, and in the end we end up with this molecule here overall. And then the last step, again we are using this nitration agent, so NO3 plus H2SO4. Of course, the tricky part here in this case is again because we can have now a lot of different substitutions happening. The para product will be one of them, but also here at the naphthalene course it will also react. So this is not quite as nice to do it in one step, but in the end you can maybe, after a very tedious workup, you can end up with this product here overall. There are probably also other approaches to synthesizing this. So if you have something and want to discuss something, you can always leave a comment, and then we can see what your solution to this question would look like.